if not, we wrap up this short assignment, and there are not many problems in there. So, what we will take up is, we've seen when we have a fundamental equation given, how to get, for instance, an equation of state or various other forms. For instance, how to express E in terms of V and D, how to get other fundamental equations. And now, if we are not given the fundamental equation, given some other pieces of information, how to construct the fundamental equation. So that is what we take up, and one of the assignment problems deals with that, two of the assignment problems. First, we take the ideal gas, and the ideal gas, the two important well-known properties are that P is RT by V, and also E is a function of temperature alone. So these are the two properties we know, and using these two properties can we construct the fundamental equation. We have probably not encountered how the fundamental equation for the ideal gas would look like, right? So we now use this. So following gives, we assume that the ideal gas has a constant Cv. So from now on, even though I won't put the subscript superscript Ig, everything corresponds to the ideal gas. Simply I have to put this as Pig and Eig and so on. So I won't do that. Everything now we're going to deal with corresponds to the ideal gas, which is basically defined by these two separate pieces of information. So Cv is constant. So I have dE by dt is Cv. That I know. Right? That's the definition of Cv. So ideal gas is independent of volume. We just have the temperature dependence alone. So I can now integrate this and write this as E minus E naught. I'll sort of put a prime, because later on I'm going to change this constant to E naught equal to Cv times T minus T naught. So I'm just integrating this. Cv is constant. Otherwise the form will look a bit more awkward, but the procedure is the same. Right? So times T minus T naught. So we can regard E naught prime as the energy corresponding to the temperature T naught, some arbitrary temperature T naught. So now I rewrite this, and as a hint that is given how to construct the fundamental equation. The hint is given, otherwise you might find it a bit difficult to proceed. So the hint is that you are supposed to invert this in the sense that I would, rather than trying to express E in terms of S and V, I would try to express S in terms of E and V. That's the hint that is given. So if you do that, ds is dE by d minus, or rather plus, d over t dV. Now you will see that this integration will become very easy. This can be written for any substance, not necessarily just for the ideal gas. The ideal gas will become easy to integrate. The integrals become separated from one another, as you will see now. So I want here t actually as a function of epsilon or E. Right? So I will do that. I will write this as or T is given by T naught plus. So I will write this further as Cv T naught, which is further written as E minus. So I have that T naught prime minus Cv T naught divided by Cv. So I'm going to call this group of terms E naught prime. That's the constant. Cv is also here a constant. T naught is another constant. So this group I am going to, just for simplicity, call this will be epsilon naught, E naught, E minus. So E becomes then E minus E naught by Cv. And so 1 over T would be Cv by E minus E naught. So that I can substitute here. So Cv integral. Now I have to integrate. So I will call this integration S naught bar, another constant I introduced. So I am integrating between 2 points. This I will call S, and I put a prime for the dummy variable of integration. So this also I integrate from E naught bar to some internality that I want, right? So, and this would be V naught bar to V, and I again take the variable of integration. That can be anything. You can replace dv prime here or even dx if you want, right? So that's a dummy variable of integration. Right? But what is important is these are, I am wanting the values of a relationship between S, E and V at a particular state of the system. Because I am going to write it as a function, right, which is variable, right? So I am fixing this at one point. This will be the running variable. So I finally get an expression expressing S in terms of E and V. Right? So you have to understand the notation. So 1 over, so this will become S minus S naught bar. 1 over T, I have already seen as Cv by, I have expressed it in terms of E prime. Cv can be taken out. Plus P over T becomes R over P. And so this would again be dv prime by v prime. So what is strictly has to be integrated together now becomes separable. So I can carry out the integration. This can be not be possible for substances in general, but for the ideal gas it turns out to be an easy way to do it. So I get S minus S naught bar is equal to Cv logarithm of, or integrate between these two limits. So the logarithm would be logarithm of epsilon prime minus epsilon naught, right? So evaluated at epsilon and, this is epsilon naught bar, that's different from that. Plus R logarithm of V over V naught bar. Are there any questions at this point? Or just go integrate? It may look unnecessarily complicated, but I just want to differentiate between the variable of integration, which is a dummy variable. I can do anything I want. Integrated between 2 points. One, what I want at an arbitrary value of S, E and V. Another again, I have integrated at some fixed point. So you could regard the entropy internal in specific quantities, specific entropy, specific internal, specific the particular state to be given by S naught bar, E naught bar and V naught bar. That's the correspondence. Right? So I am integrating from that some unspecified arbitrary fixed state to a general state at which I want the value. So you cannot avoid these constants of integration, as you will see. Right? So however, you see that there is one here, 2, 3, 4 constants I have introduced, but you can quickly see that only 2 are really needed. Right? And you see that I write this as S equal to S naught bar. Now I am going to combine all the terms which involve only the constant, and of course Cv here is a constant, that simplifies the expression, plus C, or rather minus Cv, I'm writing the denominator, logarithm of, and then minus R log V naught bar.
So by epsilon.
Huh?
By epsilon.
By?
Sir, you have written in the previous line ln epsilon minus epsilon 0 by epsilon 0 bar minus epsilon.
Yeah, E naught bar minus E naught. Because the integral is epsilon prime minus epsilon naught. The logarithm of epsilon minus epsilon naught evaluated at epsilon and then evaluated at epsilon naught bar. That's the difference. That at constant, the epsilon naught comes here. So the integration of E with respect to t, this is another epsilon that has come. So we need to distinguish. So anyway, we now see that plus Cp in the form in which roughly Gibbs had. So I'm just writing it in this way. I can leave it as it is. Because generally this makes sure that when the common understanding is that when you have a logarithm of something, it should be independent of units, right? So this form is actually quite okay in that sense. But however, this is the form in which it is sometimes written, where there might cause for confusion because that means of a quantity with units in it, right? You have to understand that there is a corresponding term there that I have now separated out. So now this entire group of terms I can call simply as S naught, just S naught. The whole group of terms, right, as S naught. So I can write this in a compact way as S equal to S naught plus Cv logarithm of. This is also a fundamental equation, but now with S expressed in terms of epsilon. But Gibbs said any relation between epsilon, S and B will count as a fundamental equation. It didn't necessarily say that one has to be expressed in terms of another. So this is a perfectly valid expression. But if I want now epsilon to be written in terms of S, that is easy to do. So for that I C is equal to S minus S naught minus R logarithm of V. And so easily you can write the final expression. So this is expressing epsilon in terms of S and B, the specific internal energy in terms of specific entropy and specific volume. This may in fact be regarded as a fundamental equation. The crucial point is depending on how we introduce these integration constants and take them out. It depends on how you do that. The forms might be slightly different. But crucially, it has the following form. You have X. I can further simplify it because you have exponential and also a logarithm coming. It can be further simplified. I just leave it as it is. And S naught and epsilon naught are the two integration constants overall that come out. Cv is the parameter of the ideal gas. Right? And important to see how it depends as the exponential of S and also exponential of logarithm of V. Probably we can try writing this. And then I have exponential of minus R over Cv log V plus epsilon naught. And then this can be written as. You see clearly the difference. I can write this as logarithm of b raised to the power minus r over cb, right? So I have exponential of logarithm of b raised to the power minus r over cb, and so the exponential times somewhat unusual form, and it can also be written in terms of the CP. So this is the form it has, and now what I want is the other fundamental equations can be easily constructed, but I will take up just one of them, A and H. A has to be expressed in terms of B and T, whereas H has to be expressed in terms of S and P. So I leave that as exercise for you to do. What I want to take up is important, the chemical potential or the specific Gibbs free energy. How is it to be expressed now as a function of T and P, right? So for that, I use the notation or the definition E plus PV minus PS. Right? So first thing to note is each one of these quantities has to be expressed in terms of PV and P. So again, all for the IDE gas. Right? So the IDE gas, E is clearly expressible in terms of I have this finally. It's a function only of temperature because it's an IDE gas. So I have that. So I have to substitute that. And PV I know is so I don't want P here, but PV is RT. Then I have T, so where we have to express S in terms of T and P to get the fundamental equation. That is very important. I cannot just leave it like that. Only when chemical potential or the Gibbs free energy is expressed in function of T and P, it becomes a fundamental equation. Right? So now S is here expressed in terms of E and so here is in terms of T and P, how would you express? From this, obviously I need to look at this. So CV log of E minus E naught is just CVT. So this would be S naught plus CV logarithm of CVT plus R logarithm of RT by B. RT by B, sorry. So what we get here, I'll write it here. Because, so write it here. This is minus T times S. Now I have an S, write S from here. Then S naught plus CV logarithm CVT. And then plus R logarithm RT by B. Now I can again, what I am going now is combine all the terms involving the constants as well as the temperature alone, so that you can clearly see. So this can be written in various other ways. CV plus R is also CP. So I can also write it. Then CP minus T S naught minus CVT logarithm CVT. This is now a very famous form for the chemical potential. So that's why I am writing it minus RT logarithm of RT, and then minus plus RT logarithm of T. So I have this, combining these two, and then I have minus T times S naught. So now I get two terms which are looking very similar. I have minus CVT logarithm of CVT minus RT logarithm of RT, and then I am left with minus RT logarithm of 1 over T, which will become plus RT logarithm of T. So, of the ideal gas, I can now call this entire group of functions as some function of temperature. And of course, it has some parameters, the universal gas constant and the Cv. So the form really clearly makes it clear where the Cv comes in, right? So clearly can be written then as, this is the most important, the pressure dependence. The chemical potential of the ideal gas is proportional to the logarithm of the pressure. So which means that as pressure goes to zero, it will become actually negative or infinity. It is going to grow up. Right? So that's an important property of the ideal gas that we would have to keep in mind. So the point to note here is that of course this could have been easily obtained maybe by just looking at this itself. So I just have RT by T. So I can integrate this at constant temperature between 2 points, 2 states with ideal gas, and I get RT logarithm of T. Right? So I'm not going to do that because we're going to get the same result. But this is more transparent because it makes clear what the function is. What you have to remember is that the ideal gas has some common properties. When expressed in terms of the molar volume, it is given by RT by T for all ideal gases. So R is a universal gas constant. It's the same for all substances. Also, the internal energy is a function of temperature. It's also a property shared by all ideal gases. Right? However, what distinguishes all ideal gases are not the same. What distinguishes one from another? So if I choose a constant Cv ideal gas, clearly the Cv of one ideal gas will be different from the Cv of another ideal gas. So that is the point that distinguishes. That appears here. Right, the Cv, this fundamental equation, it also appears here. And here, for instance, when you just leave it like this, you might wonder how, this is the common form that all ideal gases have. Clearly, this function of temperature will vary from ideal gas to another. You have to keep that in mind. These are some standard properties of the ideal gases. I've got some fundamental equations for the ideal gas which might not be very evident by just looking at this. I've shown how to construct the fundamental equations of pieces of information which by themselves are not fundamental equations, because we've already seen that this is by no means a fundamental equation. Ex, which is a function of temperature, is also not a fundamental equation. And in fact, when you express it in terms of S, you not only get dependence on S but also on V for the ideal gas itself. Right? So the ideal gas, when specific internal energy is expressed as a function of temperature and some other variable, it doesn't depend on any other variable, it depends only on temperature. But you want to express it in terms of entropy, then you cannot just stop at entropy, the volume will also come in. Right? So those things you have to keep in mind. So these give some properties of the ideal gas that you should be aware of. Any questions on this? That is capital, it's not the epsilon, it's a capital E. So you have to write, I'm not getting into that because that is unnecessary and making in another variable which I don't want to do. You can do that also, you can get the same equation. Right? So what he is saying is, why not calculate mu by right? So you can see I am not particularly in favor of that, because then first of all you have to convert everything into extensive variables. Right? It is just a cumbersome process. I can get the eligibility directly from that. Everything expressed in a specific variable. So, fundamental point of view, I always maintain that the expressions in terms of specific variables are sufficient. You don't have to really go to the extensive fundamental equation. I can also write this in terms of capital E, capital S, and capital E. I'm sorry, capital E in terms of capital S, capital B, and M, the total number of moles. But why would I NSB complicate? It doesn't have any additional information. Right? So this is a more straightforward way, easier way of obtaining the conductor. I leave it as exercise 2 of A and HR. Those are commonly available. And now what I will do is take up that other problem that gives the piece of information in slightly different form. That point out certain aspects of integration. So it is here. E is equal to 3a squared by b, and b equal to a s cubed by b squared. This is how the equation is. So neither of these are fundamental equations. So you can construct E as a function of S and B, and you also ask to get mu as a function of T and B. You can look at other fundamental equations also. So maybe the first step would be to get E as a function of S and B. So the very fact that T and B are given as functions of S and B means that I am looking at this. So from this I can infer that dE by dS is 3a s squared by b, and dE by dB is a s cubed by b squared. Minus.
So minus
is T, yeah, minus P. Minus. Now, how do we get E as a function of S and B? When we integrate, integration is made easier by noting that this is you can integrate either one of them. So, this is something that you should know, that I can integrate this, keeping B fixed. Right? So it makes it easier. Otherwise, it would be quite difficult. So I can write epsilon as integrating with respect to S. So that would be S cubed by, remember to integrate, not differentiate. That would be S cubed by 3. Right? But plus, that you have to be careful. What is that? Yes? A function of V and not just a constant E naught. That is something you have to keep in mind. Some function of V that I have to determine. Right? So I determine that by using this. Now I will calculate this. You can see the very well constructed problem that gives very good answers. Otherwise, you will run into trouble. dE by dB is, so this 3 can be cancelled. So now I have to differentiate. So a s cubed by minus 1 over b squared plus f prime of b. Right now I differentiate with respect to b. And that is equal to very conveniently. In this case, so what it means is that in this case, f prime of b is 0. That means that f doesn't depend on b and it's simply a constant, but it need not necessarily be, maybe I can get a couple of other simple problems where it's slightly more complicated, where the f prime of b, the f actually becomes the function of b, right? It implies that f of b is constant, and I can call it simply some epsilon naught. So very easily obtained. What I will leave as an exercise is to integrate this with respect to b. Then you will get some function of s. Let's call it g of s, and you can again show the t of t prime of s would be 0 in this case. But if the two are, there is a function that is not a constant, then you will get that. And we will see if we can get some problems involving that. But idea is the same. So if f of v were not a constant and f prime of v, we get some answer. So we get f prime of v is a constant. Then I just integrate and get an integration constant. Right? So this is what it is, and so the I can write this as plus a is cubed by b. Now, leave it as an exercise for you to get the other fundamental equations. You have asked explicitly to get array. Right? You can also try a as a function of t and b and h as a function of s and p. This is straightforward. I don't want to spend much more time on this. I want to move to the next topic. So, this is the inverse of the problem that we considered earlier. Earlier we have seen how given a fundamental equation, right, we get various other pieces of information. Now this is the reverse. Given various pieces of information which are not fundamental equation, how to construct for whatever purpose we might require the fundamental equation in whichever form it is required. Right? Most importantly, rather than it's important to understand how it is done. Right? But the crucial point here is probably I would say the most important out of all this is this expression for the chemical potential of an ideal gas. It's a function of temperature plus RT times logarithm of P. Right? We'll keep that in mind. We'll comment later on about this problem of pressure going to zero and the chemical potential going up, what it means. Right? And so we move from this and go back to the original problem that we proposed, namely being able to calculate changes in properties between two states. Because the whole idea of developing the differential coefficients of H, S and so on in terms of B, T and P was to be able to integrate them and construct changes in properties, which we also said that are related for the change in internal energy in an adiabatic process will give the work done or the negative work done by your body and so on. So there are various other motivation for having to calculate this. Right? So without going further into the motivation, we will get into the actual process of calculating the change. So first, the most common specification of state in terms of temperature and pressure. So I'll consider two states are given to me of a pure component, of a pure substance, whose temperature and pressure are given. That's the most common specification. Now I want to calculate some property, let's say I call it Q. Q can be either A, T, whatever. Any function of state. So basically what I want to calculate is delta U, which I'm going to define as U of so and clearly that is can be formally can be very easily written as dU by dE between stage 1 and 2. So any path between the two states 1 and 2 would suffice, and the theorem on integration of these functions says that it is independent of path because it's basically a state function. So any path between 1 and 2 would give the same answer, right, that we have to accept as a well-known result from integral and differential calculus. Right? So that then gives us the option to choose the path that would be most convenient. You may see what that means. So now I plot this, the T versus P quadrant. So I mark arbitrarily two states. Let's call this, T1, T1. So this is state 1. And state 2, let's say somewhere here, different in general. Sometimes we could have changes state variable. One of the variable temperature changes. Some may have only the pressure changes. But in general, we want to be able to handle cases where both the temperature and pressure change. So this is P2 and this is P2. Now if you look at this, suppose I have an integral a to b f of x dx. This is somewhat similar to that. You want to be able to reduce it to that. I have only one variable, I know how to carry out the integration. If we look at this, suppose let's say I choose some part, arbitrarily I can choose some part. So at every point on the path, generally I expect each of these derivatives to depend on both pressure and temperature. So it won't reduce quite to this integral, so simple like that. Then I have to parameterize the curve, the path, right? And then calculate the integral. So we are not going to get into that. But rather what I will do is to point out that there are certain specific types of paths that will actually simplify the calculation of this integral. So if I can choose, let's say, a path like this. So I want to reach state 2 by one path. There are infinite number of paths. Okay? And I will also choose another path. We call this path A and we call this, let's say, path B. Two different paths that I have chosen. Now you will see that if I take path A for instance, I am dividing it into two segments. You will see that in this segment there is a change only in pressure. So for that path, I have to consider really only the integral with respect to P. The temperature doesn't change, it is fixed at T1. And from here to here, only the temperature changes, the pressure doesn't change. So the integral over P doesn't come in. The integral over T is calculated at a fixed pressure. So let us now write down explicitly for parts A and B what the integral would look like. Suppose I take part A, right? So I'll call this maybe I can call this itself A, state A, and I'll call this state B. So I can write for part A, U of P2, P2 minus U of P1, P1 is written clearly as U of P2, P2 minus UA. That is the state. This we will say what this is, and then plus UA minus U of. All I'm doing is adding and subtracting the quantity UA, that is the property, any property, including the property associated with the state specified by the point A. So I'm sort of denoting both the path as well as the particular point by A for convenience, because I'm not going to stick with this anymore. So what is UA? It is U of P2, P2 minus U of, right, T1, T1, P2 plus again U of P1, P2 minus U of P1, P1. So clearly this difference corresponds to this segment, and this difference corresponds to this segment, right? So I am writing this difference as sum of two differences. What is the advantage of doing this? Some advantage because I am reducing rather than one term, I now have to deal with two terms. So now I will write this in the following way. Of course, I wrote the path as from here to here, that is fine. But the first term that I have written actually corresponds to this difference, right? So that can now be written. So this is a change in state, right? Where only the temperature changes, the pressure remains fixed, and it's very important to understand to keep the specified pressure properly, right? So I will write this integral as integral d1 to d2, du by dt, expressed as a function of temperature. Of course, du by dt is a function of temperature and pressure, but for this integral, the pressure is fixed at P2, and I need to mention that because it's the property is a function of both temperature and pressure, then I need to, it depends on which pressure I evaluate, so I cannot just suppress that. So to distinguish from a general function of two variables, I now say that it is a function of two variables, but it is evaluated at pressure P2. So I will, rather than separating this by a comma, I will separate them by a semicolon, so that you clearly see that this is an integral only over temperature. The pressure will also be a variable, but it is, pressure is fixed for this integral. So this is effectively like this integral. If you want, I can write this as f of x. There is no confusion with this. So suppose I simply give this integral instead of f of x, a to be f of x by d, that integral has no meaning at all. I have to specify a path connecting 2 points now on the xy plane. That has no meaning. This very much has a meaning because I am considering a function of two variables, integrating only over x, right? And I am keeping the other variable fixed, right? So that is what it is. Now the second term, which actually corresponds to this segment, with the difference between this and this, and that is clearly given by integral P1 to P2, right? du by dt. So whichever has the negative sign, that is going to come in the lower limit, that you know very well, right? So you have to be very careful not to mix up the sign. Now this is a function of P and T. This is really a function of only T here because it is evaluated at the temperature T1, and now what about path B? Right? Path B, you will easily verify that the path B, right? I have the integral over temperature evaluated at pressure P1. So I am going to write the inspection. So this is delta U corresponding to path A, delta U corresponding to path B would be integral T1 to T2. That is really the difference, this minus this, T1 to T2 evaluated at T1. And the next one will be at T2. Evaluated at T2 du by dp, integral from P1 to P2. If you are not convinced, you just write it explicitly like this and calculate, instead of UA you will have UB. So to get this, I am going to replace UA by UB and then calculate the two terms separately, right? Plus P1 to P2 du by dp at P2 dt. So clearly, on the face of it, the two intervals look different. Right? This evaluates du by dt at P2 and du by dp at T1. There is to take it that the two are the same. Two integrals will give the same answer. It might be a bit difficult to prove it actually directly from this, from here to here, but you have to take it as a well-known theorem that this is going to be the same, right? It's independent of part. Right? So what we have accomplished with either of these parts is that we have split the arbitrary path. Let's say, I can even consider a straight line path. That would again make it difficult to calculate because along the path, both temperature and pressure are varying. So rather than choose a single path, I am splitting it into two paths. One of which is a constant temperature path and another is a constant pressure path. So I can split it into two integrals. So I am integrating with respect to only one variable at a time. That is the advantage. This is a very common idea that is followed. Right? Between any two states, you can, what you have to do is to choose a path like this. Right? The next class, we will see, let's take a specific example. For instance, take U equal to E or A and see what it means. How we are going to evaluate the integral. Because it's not very general, it applies to any property. Given a specific property, how those integrals are going to look like and how are we going to evaluate it and what type of information will be required. Right? So we have to see that, we'll see that in tomorrow's class.